differential equations, which is fun. Okay, so off we go, right there. That's kind of parallel. Hey, that's not bad at all, is it? Now this point right here is going to be about x2, or it's going to be exactly x2 and then approximately y2, right? Euler says, okay, I don't know if I'm on the curve. I'm probably not, but I'm just simply going to build another line segment from x2 to x3 that has a slope where we figure out the slopes of these lines using these approximate values. So let's see. This is where I don't want to screw this up. Yeah, that's pretty good right there. Booyah. Now this value is going to be x3, comma, approximately y3. So if I'm trying to approximate a value of a solution of a differential equation, I can use this method. All right, now watch. We're going to build it right over here on the side. It doesn't take that much space at all. However, I'm going to insert some notation. Watch what notation I'm going to insert. Instead of calling this x0 to x1, x1 to x2, x2 to x3, or the differences between them like we would with slopes, I'm just going to cheat and call this h. And what we do, what Euler said, is set your h. Whatever your h is, you stick with it throughout. Okay? Now, think about this. Our first time we go through this iteration, we come up with an approximate value for y1. So what we're going to do is we're going to use very simple algebraic ideas about the equation of a line to approximate the value of y1. Well, what's the equation of a line? I know it's change in y. It's going to be y1 minus y0 equals m times x1 minus x0, right? We've done that 1,000 times. However, remember, this y1 is what we're trying to approximate. We're trying to get up here and be able to figure out what y1 is. Now, we know that this y1 and this y1 are not going to be the same. This is an approximation for y1. But watch what happens. All right, first things first. What's the slope? Well, where do we get the slope? We get it from f of xy. That's what your author refers to as the differential equation with xy plugged in. So watch how this works. I know that y1 is going to equal, or I guess it's going to be approximately equal to, because this is just an approximation, to y0 plus, now m is going to be my differential equation at x0, x0, y0, right? Because that is the slope of the tangent line at x0. Now, I need an initial point. If I don't have an initial point to start from, I am screwed. But then again, wait. What's this x1 minus x0? x1 minus x0. Ah, it's this h. That's it. It's the equation. Now, wait, let's do y2. Watch this. y2, I know, is going to be approximately equal to. Now, what did we do? Now we started at this point, x1, comma, approximately y1. I know that notation is terrible. And this little guy right there is driving me crazy. Sorry. There we go. That's a little better. Right? I've got x1 comma y1. I'm going to build a line segment to get me from approximately y1 to approximately y2. Well, I do exactly the same thing. Look. I know that the slope is going to be the differential equation plugged in not with x0, y0. Now I have to take this slope right here to help build this segment, which I know is f of x1, y1. You see what I did? I grabbed the slope at x1, I attached it to this point, and then I was off and running. Well, I know y2 is going to be y1 plus f of x1, y1, and then change in x, again, is just consistent, and it's h. And you can probably see the pattern. y3, somebody put a gun to your head in the park and made you guess? No, it's y2 plus capital F of x2, comma, y2 times h. So y sub n plus 1, let's keep it easy on ourselves, is just going to be y sub n plus capital F of x sub n, y sub n times h. And this right here is the equation for Euler's method. That was kind of easy. All right, well, let's use it on this guy. We just did this problem. Let's see what happens. I have no idea what the name of the solution to this differential equation is. I'm going to hop around here just a little bit, so don't panic. I forget what I had. I have what? Okay, so I know that y prime equals x plus y plus 1. I got to make that prettier. I'm going to have to look at that over and over. I promise you, if you're confused, you do this a couple of times and it's like, oh my gosh, Ripley, that was the easiest thing I've ever seen. Okay, so really what we're saying is f of x, y. This is notation. Remember, this guy just means the diff EQ. It's the derivative in the diff EQ, is equal to x plus y plus 1. So this is a derivative spitting out machine. You give me an x and a y, and I'll throw you a derivative. Now, let's pick a good point, and let's do a little analysis. Let's go at 1 comma 0. And here's what I'd like to do. I want you guys to think about this. It appears, let me change this. I need an ugly color that won't be easy to miss. From our last problem, do you guys agree that if I go through the process of doing this Euler's method, I'm going to start at 1, 0, and I'm going to come out here, and I'm going to build a line, and then I'm going to build another line segment, and then I'm going to build another line segment. All right? And does it appear that if I do this with these sort of stick figure curves, that I'm going to end up with an over approximation or an under approximation of what I should really, what my value should actually be? If this right here is the actual solution, well, it looks as though it's going to be an under approximation, doesn't it? Because this thing is concave up, which means these linear segments are going to end up being under the curve itself. Because those tangent lines, right? You can never curve a tangent line, as it were. Okay, so I think I'm in black. Let's see what we got here. I'm going to plug in, what do we say? Let's do this. Let's let h equal point, what do I want? 0.1, and x naught, y naught equals, what do we say? 1 comma 0. Use Euler's method. So use Euler's method to approximate. Let's go f of 1.5. Okay? So how many times are we going to have to use Euler's method? If we start at, remember this is still just an x and this is still just a y. If I start at 1, I'm going to finish at 1.5, and my height is 0.1, I'm going to use this sucker, what? I'm going to use it 5 times, right? Okay, now we're going to do it. We're going to do a lot of this on our calculator, though, so don't panic. So here's how I do this. You don't have to do it the way I do it, but I recommend that you do. All right, x naught, y naught is equal to 1 comma 0. I know that, I guess this thing's just sitting here right here. I know that y comma 1 is approximately equal to, now watch what we're going to do here. Let's write this up pretty. We're going to do, I know that y1, now this y1 is the point, it's the end point of the line segment we just created, is going to be y naught plus f of x naught. I'm only going to do this once, you guys, I promise. I know you guys hate this. Times h, which is equal to, well, y naught was 0, plus f of 1 comma 0 times 0.1. All right, so I end up with 0 plus, what we say 1 comma 0 was? Well, 1 plus 2 times 0.1. So this is 0.2 as opposed to 0.5. Boy, if it were 0.5, something would have gone horribly wrong. This is 0.2. Now, what does this mean? This implies, now think about this, we just moved over 0.1 away from 1 comma 0. So if let's go back here real quick. If I started at 1 comma 0 and I move over 0.1, what we're saying with this is, and this is how I like to write this, I like to say that x1 comma y1 is equal to 0.1 because of my h, right? Or excuse me, 1.1 because of my h. I added 0.1 to 1, comma 0.2. Now this implies that f of 1.1 is approximately 0.2. See how that works? All right, now look at this. So I've got this new information here. That tells me that y of 2 is equal to, now I'm not going to insult you guys. Remember, it's going to be y of 1, which is 0.2, plus f of 1.1 comma 0.2 times 0.1. And this is equal to 0.2 plus, now let's do this slow, 1.1 plus 0.2 is 1.3, right? Plus 1 is 2.3, times 0.1 is 0.23, 0.23. Let's make sure I did that correctly and did not screw it up. Let's see, 1.1 plus 0.2 is 1.3, plus 1 is 2.3, times 0.1 is what? 0.23, right? So 0.2 plus 0.23 is equal to 0.43, which implies, you ready? What I have is that x2 comma y2 is equal to, now what do I got here? Where I moved over a 0.1, right? So now I'm at 1.2 comma 0.43. Now here's where it starts getting kind of ugly, and we'll use our calculators to keep this easy. But remember, what this really implies, what's really the most important thing here, is that f of 1.2 is approximately equal to 0.43. Easy. All right, now, you know what? Because you guys will hate me. Let's not do up to 1.5. Let's just go up to 1.4. Do it 2 more times. I want you to do it 2 more times. What did I say? F of 1.4. All right, I want you to try it 2 more times without me helping you. And then I'll meet you back here in a second, and we'll do it together and we'll finish it up. Okay? See you soon. All right, it's like a cooking show. Kapow! Hopefully you used this equation, right? H was 0.1, right? That was going to be our change. That just means we move over a little bit at a time, 1/10 at a time, and then you simply plug in. I've got this guy right here, 1.2, 0.43. I got 0.43 plus f of 1.2 comma 0.43 times 0.1, right? Nothing to it. You end up with 0.693. This guy turns into x3. That's badly drawn. Y comma 3. I plug it in, right? I end up with 0.693. Remember, f of 1.3 is approximately equal to 0.693, right? So I just throw it in. Using this, I'm going to stick in 0.693 plus capital F of 1.3 comma 0.693 times 0.1. End up with 0.693 plus 0.2993. Gives me 0.9923. And I'm golden. Now, quick question for you. I know that this is probably off, unless my function is totally crazy. Remember, we stole this one from over here. So unless suddenly this function gets hoopty, right? Because this should be an under approximation for the actual value of the function, because this function's taken off this way, and we're building little stick figure functions like that. What if I wanted to be more accurate? What if I know that this is going to be quite a bit of an underestimation because of the shape of the curve? What if I wanted to be more accurate? What have we done before? I would just make h smaller and do more iterations from it. Isn't that clever? Isn't it elegant? It's beautiful. I mean, think about it. What did Euler do that was so earth-shattering? Oh, he used the equation of a line. Look at that. All of Euler's method comes from the equation of a line. It's so easy. It's ridiculously easy. All we needed was some notational band-aids as far as dealing with this f of x sub n, y sub n stuff. And then we needed to determine a fixed h, and off we go. All right. Not very hard. Really, just remember, probably the most important thing for you to remember is what Euler's method is used for. It's used to approximate, let's write this down, why Euler's. Why Euler's? Why do we use it? To approximate the value of an unknown diffie q. That's what it's for. That's why it's so powerful. Right? If I can't solve for whatever the heck this thing is, I can, as long as I have a fixed point, I can use Euler's method and approximate what the value is. All right? Have a good day. Thanks for listening. We'll see you in the next section. Bye-bye.